Solapur, a city of 1.1 million people, 47 signalized junctions and over 6 lakh registered vehicles. Yet today, traffic management here is entirely manual. Fixed 60-second signal cycles run whether they are 2 vehicles or 40. Traffic constables stand at junction in 40-degree heat to catch no traffic violations. The Solapur Municipal Corporation faces 3 core problems. First is the signal timing that wastes time and fuel by ignoring the actual vehicle density. Second is no parking enforcement that is slow, manual and inconsistent. Third is the parking infrastructure built on guessworks. What are our objectives? Firstly, automate the real-time vehicle counting using existing CCTV so that no new hardware is required. Our working function YOLO V8N detecting cars, motorcycle, buses and trucks etc. Second objective is dynamically optimize signal timing using reinforcement learning. Our function, the reinforcement learning, computes green signal duration as vehicle count multiplied by 3 clamped between 20 to 120 seconds. This stimulates a converged Q-learning policy. The 30-day learning curve on our dashboard shows average wait time dropping from 80 seconds to 25 seconds. The third objective is detect no parking violation automatically. Our function virtual geofencing, in which each and every vehicle is checked against this zone. If it's inside the red bounding box, encroachment alert fired and each alarm is generated automatically. Our fourth objective is emergency festival protocol, the Yatra mode. Our function Yatra mode is a one-tap feature that activates a city-wide traffic control override during large festivals or processions. Once enabled, all traffic signals switch to synchronized 45 seconds fixed cycles, ensuring a smooth vehicle flow. Fifth objective is data-driven urban planning. Our function, the ghost parking analyst, a bar chart showing illegal parking incident density by zones. This tells the SMC exactly where to build the new parking slots. So our key constants were, this is a zero new hardware, CPU only interference, open source stack with low bandwidth operations. Every function that you just saw runs on a standard laptop with no GPU, no cloud dependency and no new equipment installed at any junction. This is the architecture and system flow. The input is an open CV that reads camera feed frame by frame. Processing, 4 things happen to every frame. First is the YOLO that runs interference and returns bounding boxes. Second is the each vehicle is checked against the geofence zone. Vehicles that get inside the red box for more than 15 minutes gets a violation of no parking. Third is the RL optimizer computes the dynamic green signal time. Fourth, if the Yatra mode is active, the RL result is overridden with the fixed 45-second value. The API layer is a fast API server. It exposes 6 endpoints. The video feed endpoint streams. The traffic data endpoint returns JSON with all the current matrices. The alert log endpoint returns the full challan history. The carbon log returns the 30-day history array. Setting accepts post request to hot reload the zone's coordinate and confidence threshold without restarting the server. The front end is a React application. It polls traffic data every 1000 milliseconds, shows the live video. The encroachment alert banner listens to the Boolean flag and flashes red when true. The signal timer is a circular countdown widget that resets when the green time changes. Let me show you the working prototype. Here you can see the AI engine active in green. YOLO V8N is loaded and the CCTV feed is running. Live traffic density is showing 14 to 19 vehicles detected in this frame. The RL green signal time is 42 to 57 seconds computed dynamically from that count. Eco Niyantran shows 0.1 kilograms of CO2 saved this session compared to the legacy 60 seconds baseline, and the signal timer on the right is counting down the real time. This is the live feed. You can see green bounding boxes on vehicles in normal traffic lanes, and here is the no parking zone red boxes. The no parking zone label is drawn directly on the frame by OpenCV. When a vehicle enters the zone, the red banner fires, encroachment detected, and each alarm is auto drifted. The alert page logs every event, time, zone, status, and the auto-generated each alarm number or proof of number parking if car is parked there more than 15 minutes. This is the paper trail SMC needs for encroachment. The camera feed page shows the full stream with camera sector tabs for different chokes. So watch what happens when I toggle the Yatra mode. The header turns the amber, the signal locked to 45 seconds, and the banner announces emergency protocol active. And here the setting page. I can change the zone pixels coordinates live. This map directly to the video frame. When I hit save, the backend picks up the new zones on the next frame. No restart is required. Down here, the RL optimizer learning curve showing 68.7 wait time reduction over 30 days, and the ghost parking analyst recommending where SMC should prioritize new parking infrastructure. The most important question of Solapur Municipal Corporation is, can this actually be deployed? And the answer is yes, at a fraction of cost of traditional traffic management system. Traditional adaptive traffic control system like Scoot requires inductive loop sensors embedded on road surface, that is 8 to 15 lakh rupees per junction plus 2 to 5 lakhs per year in the software licensing. For 47 junctions in Solapur, that's 4 to 7 crore rupees minimum. SMC Niyantran requires one Raspberry Pi 4 per junction, that is 8,000 rupees. Connecting it to existing CCTV camera via RTSP, zero road digging and zero sensors installation. Total cost of 47 junction will be under 4 lakh rupees, that is 95% of cost reduction. Replace the rule-based RL optimizer which was used for prototype as large real data to train model with a train deep queue network agent using real pilot data, and add multiple junction green wave coordinates so multiple signals can make coordination. On bandwidth, the MJPEG stream is compressed to 80% JPG quality. The API polling runs at 1 Hz. The entire system runs on low or fluctuating network, no cloud dependency, edge processing only. So what makes SMC Niyantran genuinely innovative, not just technically but for Solapur specially? So first is the enforcement learning based adaptive signal controls. Our system doesn't rely on fixed timers. It learns signal timing directly from traffic patterns like vehicle density, queue length and conjunction flow. Over time, it continuously optimizes signals to reduce waiting time and improve throughput, specially tuned to Indian traffic behavior and not just idealized models. Second is that it's only traffic platform we found that has a festival mode built into its core architecture. Yatra mode is not just a workaround, it is designed feature for Solapur's unique civic reality. Third is the virtual geofencing with no GPS. Every no parking zone in the city can be defined, adjusted and enforced in a real time from a web browser. No physical markings and no sensors installation. A constable sitting at the control room can move a geofence in 10 seconds. Fourth is the ghost parking analyst converts raw violation data into a infrastructure investment recommendations. This transforms a traffic enforcement tool into a urban planning intelligence system. Fifth is the honest sustainability counting. Our carbon tracker doesn't just show a green number, it computes saving against a real baseline using real commission factors and updates every frame. So that was all about SMC Niyantran. Thank you.